For us, we're going to try and do the theoretical derivation of moment of inertia. And there's two different ways to do this. You can do the moment of inertia calculation of a point mass by doing a summation. Now, the thing about doing a summation, and this is, again, the point mass calculation. This is often used for situations in which you have objects that are separated by large distances relative to their own size. For example, you could do a point mass calculation for the moment of inertia of the Earth-Moon system. The Earth and Moon are separated by a very large distance relative to the size of the planets, so the planetary size themselves contributes less to the actual moment of inertia, while the separation distance between the planets carries a lot more weight. Now, although that is true if you need the moment of inertia of the Earth-Moon system, which for some things you do, if we're trying to find the moment of inertia of some basic objects, they are just a continuous object. You have a uniform or relatively uniform density, and we might be trying to find out what their moment of inertia is if we're trying to spin them about a particular axis. Now, we can't treat this whole thing as a single point mass if we're trying to find its moment of inertia. But we could take an object like this and break it up into pieces and get an estimate for what its moment of inertia will be. This is how you can use the point mass calculation to get an idea or an estimate of an object's moment of inertia without having to use calculus. But you will have to kind of assemble some parameters in order to make this calculation. We're going to treat this like it's a meter stick, like it's very long compared to its width or its depth. And we'll give it some parameters. We'll say that the length of this object is L, and M represents the mass of the object. Now, if we're trying to figure out its moment of inertia, the other thing to consider is moment of inertia changes depending on where the axis is placed. So if we want to find its moment of inertia, we must start that problem by knowing where the axis of rotation is that we want to use. So let's say this might represent a baseball bat and you're going to rotate it about its end. We could try and find the moment of inertia of this rigid rod about one end. Or if you're going to spin it about the middle, it's a helicopter blade, then we could try and find the moment of inertia of an axis of rotation about its center. Again, these would just be estimates, but it gives us a pretty good basis for what to expect for the object's moment of inertia. Now, before we launch into this too much, I want to point out that moment of inertia tries to tell us the distribution of the mass of the object. That's what it's trying to tell us. It's trying to boil it down to a single number that tells us how much of the object's mass is located away from the axis of rotation. We know the more spread out it is, the bigger the moment of inertia. So, as an estimate goes, we're going to take this object and break it up into multiple pieces. Now, I'm going to tell you before we get started, the moment of inertia of a rigid rod about one end is 1/3 ml squared. This is the value you get from doing the calculus on the problem. And we'll get to that in a bit, but we're going to see if we can't estimate it using the point mass process. Now, we're going to break the object up into multiple pieces. And all day today, I've been doing 10 pieces because I feel it's enough to get the point across, not too many to be too laborious, but also enough where we start getting reasonably effective numbers. You could try and do this with just 2 pieces or even 1 piece, but you won't get close to the right answer. So 10 pieces seems to be enough. So we'll break this up into 10 pieces. And I would encourage you to do the same. I'm taking and breaking it up into 10, what I hope will be equal looking pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 kind of equal looking pieces. What is the length of one of these pieces? No, it's not a meter stick. Okay, so I'm going to use fractions, but 0.1 or 1/10 of L would be the length of one piece. What is the mass of one piece? I'm sorry, what do you think the mass of one piece would be? 1/10 m. If the whole piece is m and we're breaking up into 10 equal pieces, I expect each piece to be 1/10 of the mass and 1/10 of the length. All okay so far? If it's of uniform mass density, then each center would be where the center of mass is for that piece. Now what we want to do is a summation. And to do the summation, we have to understand what these pieces are about. M represents the mass of a piece. Luckily for us, all of our pieces are going to be the same mass, but you understand, if something got heavier as you went from one end to the other, then the mass might be changing. And also, R represents the perpendicular distance from the axis to the piece. Again, R represents the perpendicular distance from the axis to the piece. So let's assemble our summation. Now I say let's, but I actually want you to do this. I think you're probably smart enough where you could come up with a summation. You're going to be adding together 10 values because there are 10 pieces of mass. So can you start to assemble what this summation should look like? If we're looking at the first piece, M would be 1/10 M. And I'm pretty sure R would be 1/20 L squared. Right? Did you go to the next term? Because the next term I have to add another 1/10 L, right? What does that give us? What's that? 3/20. Are you seeing a pattern yet? Maybe go one more just to make sure you know what the pattern is. 5/20. Do you notice that every single term has a 1/10 M in it? And then every single term has a 1/20 L squared? If it were me, I would just factor those out. What would be left in here? 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared plus 11 squared plus 13 squared plus 15 squared plus 17 squared plus 19 squared. Do we keep going? No, I'm pretty sure that's 10 different pieces, right? And right, we only broke it up into 10 pieces. All right, figure it out. Get a number. This should give you something times ml squared. we know our answer is going to have ml squared in it. First, all of this, I better get the answer section. We're going to need an extra step for this class. All of that is 1330. I'm not going to explain how to do that. That's just adding together some numbers, okay? But also I've got out front here, I've got, let's see, 10 times 20 squared is 4,000. ml squared times 1330. Just doing arithmetic here, folks. Some of you forgot there's all of this out here. But also, some of you got weird stuff for that, and I don't understand. I don't know where 80 came from, but that's on somebody's paper. By the way, what is 1330 divided by 4,000? 0.3325 ml squared. Considering we're supposed to be comparing this with a third, our estimate comes out to be pretty close to what a third would be, right? Down to the fourth decimal place. I would assume that if we did 20 pieces instead of 10, it'd get even closer. And this is doing infinite number of pieces. This is what we got by just doing 10 pieces. But there's some trouble here, so I think you guys need to demonstrate a little more proficiency. We're going to try again. And I'm not going to change very much, but I'm going to give you less help this time, and I'm going to call you out if you get it wrong. Let's move the axis of rotation to the center. Same thing, same rod, same specifications. We're just moving the axis of rotation to the center. This is just for you to practice maybe your, your arithmetic. I will tell you the answer, however. If you're looking at the center, the moment of inertia of a rod about its center is 1/12 ml squared. So you try this again and help. Most of what you need is still sitting up there. What I did was make a new axis of rotation. So again, what you have to do is it's a summation. So I have to take each piece of mass that's here, multiply the size of the mass, 1/10 m, times its distance from the axis of rotation. So like this piece, its distance away from the axis of rotation is 1/20 L. And I have to do that for every piece on both sides. Okay? Same thing that we did a moment ago, but we have two sides to deal with now. I am hoping that you find a certain shortcut. Like, can we agree there's going to be two of these? Two that are 1/20 away? And there's going to be two that are 3/20 away? And two that are 5/20 away? But we're going to stop when we get to 9, because that would be the last piece. So can I just add up those 5 and then multiply by 2, since there's 2 of all of them? All right, that's good. So you got a 3,300 here. And let's see, 3,300 divided by 4,000 gave you 0.0825. And when we compare that to 1/12, .0833 repeating. Close. Okay, so the point mass process can get you close. Can't get you right on. it can get you close. However, I want you to be able to get right on. And to do that means you have to do an infinite number of pieces. So to do an infinite number of pieces, we're going to have to use the voodoo of calculus for that. So, no difference. We're gonna treat this kind of the same as before, but we are going to have to make some concessions. I want everybody to understand that people who have had calculus here really don't have much of an advantage. You see, the expression to find the moment of inertia is definitely a calculus expression, but it's not the integral that is difficult to do. In fact, in this class, for this unit, it will never be anything more than the power rule for all of the integrals. However, it's setting up the integral that's tough. Now, I'm gonna level with you. I'm gonna be as clear and direct as possible. No one ever showed me how to do this. I had to come up with a method and figure it out myself. They just assumed that you could do it. I don't make that assumption. I'm gonna assume that you need guidance. Calculus will not teach you how to do this, by the way. They'll get you the last step, integrate to get your answer. But they don't assemble the integral, and assembling the integral is what's challenging. Those of you who are thinking about E&M next year, talk to the people in E&M. You'll know assembling the integral is the hard part. Acting on it, that's not the hard part. So assembling is where we want to work. And I'm going to show you what you must do to assemble this. Okay, we're going to first start out with the same dynamics as before. We have a long rod of length L and mass M, and we're going to assume it's of uniform mass density. Now, what that means is that if we pick any piece out, if we take two pieces that are the same size, say one piece from here and one piece from here, if we take these two pieces, they would have the same mass if they are the same size. Does that make sense? So it's of uniform mass density. Now, if they told us that that wasn't true, that it got heavier as you go from one end to the other, well, then the density wouldn't be uniform, and we would have to do something with that. We'd have to do something with the density. But if they tell us it is of uniform mass density, then we can just assume every piece is identical, just like we did the last time. So, choose or be given your axis of rotation. We're going to use the axis of rotation about the end. So we're spinning it about its end, like a baseball bat or a golf club. Again, we're going to say that it's very long compared with its width and its depth. So we're going to assume that differences this way don't matter very much, but differences this way matter the most. Okay? This object is considered to be a one-dimensional object. Right? It's about the mass being spread out in the x direction, not in the y direction. Everybody okay so far with that idea? All right. So, step one, identify your axis of rotation. Not a problem. Step two, identify and draw in a piece of the mass. So what I mean by this is to literally draw a piece and state that this is our piece of mass and every piece of our object is going to be of the same size. Okay, so I'm going to label it dm because that's what dm means, delta m, a piece of the overall mass of the object. If I sum all of the dm's, I get the total mass of the object. Right? This This integral would be to add up every piece of mass. Well, at the end of the day, that would just be the mass. Okay, so delta m dm represents a single piece of the mass. This part's a little bit harder. Easy for one-dimensional. Harder as we get to more complicated geometries. You want to find a way or choose an appropriate set of variables to point out the piece of mass. Yeah, I can. We'll it out running over any cars that are over here. Now, when I say point it out, I quite literally, we want to find a way to use some kind of geometric terms to point out where the object is. It's probably going to take one value for a one-dimensional object, two values for a two-dimensional object, and three values for a three-dimensional object, right? For this one, I can probably just use x and say that my object is x away from the axis of rotation. But if it was a two-dimensional object, I might need an x and y, or an r and a theta, right? I'm choosing coordinates that can point out where the object is. Now, you want to test to make sure you can address every mass. Meaning, can I, using just x, point to every single piece of the rod? And I think I can. I can say the first piece is located at x equals 0, and the last piece is located at x equals L, and there is a location for every piece from 0 to L. So I think I passed the test. Now, question 5, a little bit weird, but it's okay. Describe the size of your piece using your variables. So, for example, if I want to describe how big this piece is, well, I go out a distance x, and my piece is a little bit more in the x direction. It's delta x. So I'm going to say my piece, the width of it, is dx wide. It's a little more in the x direction. I just need its length, because we said the width and the depth will be the same for every piece. So we're describing the length of this object using the variable that points to it. So if the thing was two-dimensional, we might describe an area, and that might be its length, dx, times its width, dy. You see what I'm saying? So for each shape, it will depend on whether it's one-dimensional, two-dimensional, or three-dimensional. We're only going to do one- and two-dimensional problems. Now this part's a little bit harder. We want to find a ratio, a way of comparing the mass and shape of our object to the mass and shape of our piece. For a one-dimensional object, it's pretty easy. We're just going to use a ratio. The mass per unit length has to be the same for the whole thing and our piece because it has uniform density. But we're trying to find a way of relating the mass and the shape for the whole object to our piece. So what we're really saying is that every piece has the same density as the whole thing. This is the density of the whole thing. This is the density of our piece. If it was a two-dimensional object, then it'd be mass over area equals dm over dA. All right, so you can imagine what this would look like if you were dealing with a two-dimensional or a three-dimensional piece. But our object is one-dimensional. Once you do this, solve for dm. So dm is m over L dx. Okay, good so far? All right. So here we go. We're going to finish the problem. Or try to. Maybe. Now you need to assemble your integral. R represents the perpendicular distance from the axis of rotation to where our piece of mass is. Can we agree that in this case it's x? So I put x squared. We spent most of our time figuring out what dm is. That's what the whole setup was about. Being able to put in that dm is m over L dx. Now we need to tell the integral to begin at the first piece and end at the last piece. The execution of this integral should give us the moment of inertia. Now, to execute this integral, anything that is a constant gets brought out front. M and L are constants. They are the same for the whole thing. So just like in the summation where we brought M and L out front, we'll do the same thing here. This part is the only part where the calculus kids have an advantage because they can do this integral. But so can you, right? You notice that it's a polynomial integral, right? X squared relative to dx. So I add 1 to the exponent and divide by the new exponent. Now we have to substitute in our limits. And now simplify. I've got an L cubed divided by L is L squared. You guys see it? So, bless you, 1/3 ml squared. All right, well.